Hey guys, this is Mrs. Hartman, and this is Pre-Cal Chapter 5. We are working on equations, and in this lesson, we are going to take a look at rational equations in Lesson 2. Our biblical integration for this unit is this. God allows us to have challenges in life, but He also equips us to face them. Becoming familiar with useful terms is like putting on armor to face algebraic problems. We're building up the foundation so that we can tackle more difficult and more challenging problems. And all of this fits into that worldview study that we did at the beginning of the year and that we've talked about throughout, that we are using the skills and gifts and talents that we have to follow through in that creation mandate, to take care of other people, to take care of creation. And being able to solve math problems has fixed a lot of problems and created safety equipment and just done a lot of good things to help take care of creation and the world. Our lesson objective for today is that you, the student, will solve rational equations and use domains to check the extraneous roots of rational equations. Now let's talk about some vocabulary here. We know that rational numbers, you think about rational numbers are ratios. Another word that we have for rational numbers is fractions. So 3/4 is a rational number. 7/1 is a rational number. It's a ratio of two different parts. So another word for rational numbers is fractions. A rational expression is an algebraic expression that is the ratio of two polynomials, p of x to q of x, where q of x cannot equal 0. So an example of a rational expression might be x minus 1 over x, or x squared minus x plus 3 over x plus 7. Pardon my handwriting there. Those are rational expressions. And think for a second, why can the bottom polynomial not be 0? Well, if x were 0, let's take this one for example. If x were 0, we would have -1 over 0, which we know is undefined. And so we can't have our bottom polynomial or the bottom of our rational expression be equal to 0. So that is a rational expression. A rational equation then is an equation, which means we have something equal to something else, that contains at least one rational expression. When we are solving for rational equations, we're going to find the least common multiple of the denominators and multiply both sides by it. It is necessary to check all roots because we have the possibility that we could introduce extraneous roots through multiplication, through squaring terms and taking roots. Right? Think about when you were working with fractions. If you wanted to add, for example, 1/2 plus 1/3, and you'll see this on the next screen as well. The first thing that you had to have was a common denominator. And the way that you did that was actually multiplying by a common denominator. Okay, so the common denominator of 2 and 3 is 6. That was our common multiple because 2 is a factor and 3 is a factor. And so that was 6 was our common denominator. Write that here. Least common denominator. You're going to see the same thing when we work with rational expressions, that we're going to look at the individual factors and find a common denominator. So let's take a look. Okay, you have that 1/2 and 1/3 there. All right, so we have 3n over n minus 5 equals 3n plus 1 over n minus 4. And the first thing that we need to do is find the common denominator. So the denominator on this side is n minus 5, and the denominator on this side is n minus 4. And the way that we find the common denominator is multiplying those things together, n minus 5 times n minus 4. So there's our common denominator, n minus 5 times n minus 4. Now we could go ahead and multiply that out and get n squared minus 9 squared plus 20, or we can just leave it as individual factors. It's actually a little bit easier to leave it as individual factors. So we're going to multiply both sides here by n minus 5 times n minus 4. I'm going to put some parentheses around. So this was our original equation here, and we're going to multiply both sides by the two factors of the common denominator. And we do need to take this and multiply it by here, and take this and multiply it by here. Well, when we're multiplying, This is n minus 5 times n minus 4 over 1, by the way. you can see that this has an n minus 5 on the top, and there's an n minus 5 on the bottom. So we could multiply them out and then cancel, or we can recognize that those are going to cancel each other out. So we can go ahead and cancel at the beginning. That just leaves us 3n times n minus 4. And over here, we have 3n plus 1 times n minus 5 and n minus 4. We could multiply all that out. It would make a lot of work for us, or we can recognize these are going to cancel right from the beginning. So we're taking 3n plus 1 times n minus 5. So that's the quicker and easier way to do that, instead of multiplying everything out. We then get 3n times n minus 4 on the left, and 3n plus 1 times n minus 5 on the right. We are going to have to multiply those using distribution, FOILing, the box method, whichever method you prefer, but we do need to multiply to get rid of the parentheses. And when we do that, we get 3n squared minus 12n equals 3n squared minus 14n minus 5. We're then going to go ahead and solve for n. We can eliminate our n squared terms here by subtracting 3n from both sides. We eliminate our n squared term, and then by combining our n terms and our constant terms, we get 2n equals negative 5, which then means that n equals negative 5 halves. We are going to solve, and then we're going to check our work. We'll plug it back in, because we always want to make sure that we haven't introduced any extraneous solutions there, and n equals negative 5 over 2 does check in the original equation. If you plug that into both sides, what you're going to end up with is 1 equals 1. That is a true statement, and so that does check out. Now, the process of checking may seem a little bit tedious. It's acceptable, but it's not always necessary for identifying extraneous roots. We only need to check that the value is in the domain of the rational expressions. So in other words, if the answer does not create a 0 in the denominator, then it's not extraneous. So in example 1, if you go back, when we plug in negative 5 halves into those two denominators, when we plug it in here and here, it doesn't cause either denominator to equal 0, so it's not extraneous. So we wouldn't have to necessarily plug it back into the whole equation. We could save some time by plugging it in just into the denominator. All right, so let's solve and check this one. 2x minus 1 over x plus 3 plus 1 over x squared plus x minus 6 plus x minus 4 over x minus 2 equals 0. The first thing that we want to do is factor all denominators so we know what our individual factors are. This one's already been factored, and this one's already been factored. This middle term, though, has not been factored. So let's factor that so we know what our individual factors are. So our middle term factors to x plus 3 and x minus 2. Okay, once we have that factored, we can determine our least common multiple. So let's look at our individual factors. Okay, we have x plus 3 is one of our factors. And we don't need to list it twice because it appears twice. We just need to list each factor that appears. So x plus 3 is one of the factors that appears, and x minus 2 is one of the factors that appears. So our least common multiple, or our lowest common denominator, is x plus 3 and x minus 2. Those are the two factors. So we're going to multiply each term, or both sides of the equation, so each term, by that lowest common denominator. So on the left there, we'll put a bracket, and we're going to, again, multiply each term. So we've got to distribute that to each term. And when we multiply that by the first term, you'll see that our x plus 3's will cancel. So we're left with just x minus 2 times 2x plus 1. In the middle term, these will both cancel out our denominator, so we're left with just 1. And in our third term, the x minus 2 will cancel, leaving us with 4 times x plus 3. So there's our first term, our second term, and our third term, and all of that is equal to 0. We'll then multiply those out using FOILing or whatever method that we need to eliminate the parentheses and combine like terms. So here it is multiplied. 2x squared minus 5x plus 2 plus 1 plus x squared minus x minus 12 equals 0. Let's go ahead and combine like terms. we get 3x squared minus 6x minus 9 equals 0. That is a quadratic, so that should be a signal to you that you should try factoring. And factoring does work for this. We're going to factor out a 3. So we can take a 3 out of each term here, which leaves us with x squared minus 2x minus 3. And when factored, we get x plus 1 times x minus 3 equals 0. We'll then set each of those equal to 0, and we get x equals negative 1 and x equals 3. We do need to check our solutions here to make sure that they are not extraneous. If you remember, our denominators were x plus 3, x minus 2, and x squared plus x minus 6. And when you plug in those numbers into those 3 different denominators, none of them equal 0, so neither of our roots is extraneous. All right, guys, that is it. The most difficult part of this is probably going to be finding the common denominator. So remember that when you're trying to find the common denominator, factor all the denominators first, then list each of the factors that appears. You don't need to list it if it appears more than once. Just list each of the factors that appears. Then multiply each of your terms by those factors, by the common denominator. You'll then solve for x and then go back and check to make sure you don't have any extraneous solutions. So today we solved equations, rational equations, and we used domains to check the extraneous roots of rational equations. If you guys have any questions, be sure to write those down and ask me next class.